Good afternoon, everybody. Let's get started. So for announcements, we will perform Lab 3 this Friday. So be sure to take a look at the lab assignment coming up for this Friday. We're going to be working with the microcontroller, and so I'll give you some tips on that in lab, but it's good to have a familiarity with the lab before showing up at lab. So take a look at that assignment. There is no homework due this week. Homework will be due next week. That due date, due time is posted on Canvas, so please take a look at that. So during the last class, we started the test and measurement topic, and we worked through multimeters and measurements of diodes. And so today we're going to continue the measurement topic for probably another 2 lectures, and then move on to the next major topic. But I want to cover some what I think is useful information, so when you go into lab, you'll be able to use the equipment more effectively. So we talked last time about measuring diodes. I wanted to move on to using a multimeter to measure frequency and duty cycle. So many of these handheld multimeters, like this one's probably $20 or $30. They're really not all that expensive. It's a pretty low cost to pick one up, but many of them will do measurements like frequency and duty cycle. And so what they measure when you're set to the either frequency or duty cycle setting is they measure zero crossings typically. Okay, so you have to have an AC waveform applied to the common and the input on this multimeter, and then the multimeter is going to sense the zero crossings of the waveform. Okay, so you set to either, well, you can set to hertz in this case, which is frequency, or percent, which is duty cycle, and then select between those two measurements. So if you have a waveform that looks like this, a rectangular waveform that varies between -1 volt and 1 volt, and it's periodic, has a regular period, it may not be 50% duty cycle. It may be whatever duty cycle it is. But to measure a waveform that has a DC offset, you actually have to use a capacitor to block the DC and pass AC. Okay, so if you set the multimeter to measure frequency, it'll measure frequency of this waveform. If you measure the duty cycle, it'll measure the duty cycle. But if you have an output, let's say, of a microcontroller, like the Arduino you're going to use in lab, you're going to produce a waveform that varies between 0 volts and 5 volts with a given frequency and a given duty cycle. But there aren't well-defined zero crossings here. In fact, in theory, there aren't any zero crossings. You're going between 0 and 5 volts, but noise on the signal may cause some zero crossings. So what you need to do is actually block the DC so that you can produce a waveform that goes between roughly -2.5 volts to 2.5 volts. The capacitor, depending upon its capacitance value, is going to distort that waveform a little bit. You might get some kind of exponential rise and exponential decay because of the RC time constant. But if you use a large enough capacitor, that shouldn't be an issue. So you would be able to measure the output of an Arduino, 0 volts to 5 volts, right? A pulsed waveform like this, using this capacitor between the multimeter and the Arduino's output port here. Okay, so that's just a tip. If you're trying to measure a waveform with a DC offset, its frequency and duty cycle, then, and it's not working, try putting a capacitor to block DC. Okay, so that covers the measurements that I wanted to talk about that multimeters do. Let's move on to oscilloscopes. So this is the oscilloscope that you have on your lab bench in the ITLL. Oscilloscopes measure and display voltage versus time. So you can imagine putting standard axes of a plot on the oscilloscope. Voltage is the vertical axis, time is the horizontal axis. Okay, and measurement applications are wide. There are many measurement applications for an oscilloscope, but typically you're using an oscilloscope to either view a periodic waveform like the sine wave. It could be a triangle wave, it could be a square wave. You might be looking at the shape of it. You might be looking at different characteristics of that waveform. Maybe the rise time of a square wave, or maybe the overshoot of a square wave, for example. But you can view periodic waveforms. You can also view snapshots of non-periodic waveforms. So let's suppose you have a burst of data coming out of a device like a microcontroller. You have a burst of data. It might be, let's say, eight bits of data plus maybe some leading bits and trailing bits, and you want to see that burst on the oscilloscope, and it's non-periodic, right? It's just a burst. You can set up an oscilloscope to trigger off the beginning of that waveform, capture a certain amount of time, and then hold it on the screen so you could see the bits of data included in that waveform. Okay, so it could be something like that, where it's a non-periodic waveform, but you want to view voltage versus time. You can measure periods and frequencies of periodic waveforms. You can measure min voltage, max voltage, RMS voltages. And often you can do this with automated measurements built into the oscilloscope. You can also measure features of waveforms using cursors. I'll show you an example of using cursors on this oscilloscope. Okay, so you may want to measure, let's say, like in your project, a pulse width modulated voltage applied to a motor. So an oscilloscope is a good piece of equipment to view that. You can measure the pulsed voltage out of an infrared RPM sensor. So you have in lab a proximity detector or an obstacle detector that you're using to detect blade crossings for your project. You can measure the output voltage of that sensor and then do some conversion from, let's say hertz, measure the frequency, convert from hertz into RPM using the number of blades and a conversion factor there. And so the oscilloscope is useful for that. You'll notice some vocabulary used for oscilloscopes that doesn't seem to apply. You don't typically use this vocabulary when you're talking about just plots of voltage versus time. But today's oscilloscope terminology and the settings for the oscilloscope, they really derive from some early analog oscilloscopes and really how they worked. Okay, so you'll see terms like per unit or per division units, like volts per division, time per division. You'll see terms like sweep and triggering and hold off and position. And so these derive from the old oscilloscopes, and then they slowly became modern, and now we have digital oscilloscopes, but we still use the same controls and a lot of the same terminology as the early oscilloscopes. Okay, just like today we still use terms like dialing a phone, and phones don't have dials anymore, but we still say we dial a phone. So some of these old terms kind of stick around. Let's talk about setting up the axes of an oscilloscope. Let's talk about the horizontal axis, which is the time axis. So you use the horizontal settings of an oscilloscope to control the scale of the time axis. So here is a zoom in of the horizontal settings of this oscilloscope. And this is one particular model of an oscilloscope, but most oscilloscopes use the same or similar terminology with the same or similar buttons grouped like this. Okay, so time axis is often specified in seconds per division. Okay, so it might be milliseconds per division, microseconds per division, nanoseconds per division. And this is one division on the plot. So you usually have 10 divisions across the horizontal span. And so there's usually a knob that controls this. So here you can see that, well, this oscilloscope actually labels a few of the vertical lines to show the horizontal scale, but here's 0, here is -1 millisecond, here's 1 millisecond. So one division is 0.5 milliseconds or 500 microseconds. So this scope is set on 500 microseconds per division. And to change that, you use the horizontal knob. So, this knob says nothing about time, right? It just says horizontal, but that's what you use to adjust the time scale. Okay. So not only can you adjust the time scale in time per division, but you can also adjust the position. So this position, if I move the position left or right, it'll slide that waveform left or right so I can view different features possibly. Okay, so right here you can see that there's this triangle up at the top, and we'll talk about triggering, but that's where the scope was triggered, and that's time 0 on this plot. And you can adjust the position. You can move that waveform left or right by moving this position knob. And it says push to 0 if you want to center the waveform at center time 0 in the middle. You push that button in, push that knob in. Now you'll notice that we have time 0, time 1, time 2 milliseconds. We also have negative time, -1, -2. So we're working with causal systems, but what's happening here is the oscilloscope is actually sampling all the time. And so when you trigger the oscilloscope or tell it to start plotting at time 0, it actually has in memory negative time. So it can go back and plot negative time. All right, let's look at the vertical axis and controlling the vertical axis. So oscilloscopes often have multiple channels. You typically have a 2-channel oscilloscope or a 4-channel oscilloscope. Those are pretty common. And each one of those channels measures a separate voltage. Okay, so you can measure on this 2-channel oscilloscope, you can measure 2 voltages and plot both of those voltages on the screen. And you use the vertical settings to control the scale of the voltage axis. And you can control each channel's scale independently. Okay, so you could zoom in on the vertical axis to a very small waveform, small in amplitude, and for another channel you could zoom way out, maybe it's a larger voltage, and you can compare those 2 waveforms. Voltage is often specified in volts per division. So here's an oscilloscope plot, again, voltage versus time. And one division here is 2 volts. You can see I have 0 volts right around the center of the screen. And that's divided up into this grid in 2 volts per division. So there's usually a scale knob. So here, vertical scale. This is the scale for channel 1. This is the scale for channel 2. Both of those control the volts per division for their respective channels. So that's how you control the scale. And there's also a position knob. So these 2 knobs, one for each of the channels, control moving that waveform basically up and down. So you can position it vertically on the screen. Okay, so if you have one waveform that has 0 DC offset, like this waveform here, and then you have maybe that square wave out of the Arduino, and it goes from 0 to 5 volts, and you want to center that on the screen, you can adjust its position independently. And then different oscilloscopes work different ways, but typically on these digital oscilloscopes, if you press a channel button, it will put that channel's voltage on the screen. It will plot it. If you press that same button again, often it removes that channel. If you press, let's say 1 and then press 2, you'll see both channels on the screen. And if you want to remove number 2, press number 2 again. And often you can press these buttons to see on the screen of the oscilloscope the vertical settings and options. So you just have to, I'd say read the manual, but usually you just sort of take some measurements, look at the work with the oscilloscope, try to find the functions and the features you know it should have, and then if you can't find the features or functions, or you don't understand some setting, then dig into the help. Okay, so we've covered horizontal axis, time axis, vertical axis, voltage axis. Let's talk about triggering an oscilloscope. So the trigger functionality of an oscilloscope synchronizes the voltage and time axes that are displayed on the screen. So the waveform has to be synchronized, let's say in time, because if you just sample a waveform and show it over and over again, you're gonna see like random starts of that waveform, and it's going to look like garbage. You're not going to be able to measure period or see the shape of a waveform that's periodic. And you use the trigger settings to control the voltage level at which the scope will trigger. Trigger means start the sweep, start the plotting of the waveform, or define where time zero is. So you can control the voltage level of the trigger and the slope of the voltage crossing that trigger. And that's how you synchronize the waveform on the screen so you can view a periodic waveform. So when a measured voltage, so you have, let's say, channel 1, you're measuring a voltage, and it's this sine wave. When that sine wave crosses the trigger voltage level, that point, that sample, will be considered time zero on the screen. So here's the trigger voltage. All right, it's set at 0 volts. And so right when this waveform crossed 0 volts, the oscilloscope is considering that time zero. I say, why didn't it pick the other crossings? Well, the oscilloscope is set to, at some point in time, start sampling the waveform, and the next time that the voltage crosses that trigger level, then call that voltage or call that time zero. So you can also define the slope at which you want the trigger to start showing the waveform at time zero. So the slope setting defines whether 0 seconds should occur on a rising or falling slope. So here I'm triggering on this trigger position, so that's 0 seconds right there at this trigger voltage, and I was waiting for, the scope was waiting for a rising slope, a positive slope. Okay. And you can define a negative slope too, right? A negative slope would be detecting a fall from a positive voltage to a negative voltage across 0, or from a higher voltage to a lower voltage crossing the trigger voltage. And the channel setting defines which channel should be used for the trigger voltage. So you can have, let's say, you're looking at 2 waveforms. Maybe they have the same frequency but different shape. And you're looking at those waveforms with channel 1 and channel 2. Well, you can trigger off of channel 1, or you can trigger off of channel 2. And so you can select that. So in this case, looking at the screen, right, I've already highlighted this, but here's the trigger position on the scope that you're using in lab. When you see this triangle here, that's the trigger position. Here's the trigger voltage. There's a little T, and you'll see a dotted line across. It's hidden behind this pink line here. You'll see here's the trigger slope indicated. You see a low, and then a rise, and then a high with an arrow going up. That shows you the trigger slope as a symbol. The trigger channel is channel 1, so I've got the sine wave off of which I'm triggering applied to channel 1, and I'm triggering off of that. The trigger voltage is 0 volts. Okay. So let's look at some examples. So on the right here at the top, I have a waveform that's periodic, and it's triggered properly so I can view that waveform. On the bottom, same thing. It's triggered properly. I can view that waveform. On the left, this is the same waveform, but I'm actually not triggering off that waveform. I'll explain that in a minute. And you can't really view it. It's hard to measure the time between peaks or the time between zero crossings so I can determine the period. On the right, these two waveforms, I can. Okay, so the trigger voltage needs to be set within the span of a measured voltage. So looking up here in the upper right, I have the trigger voltage set to right where this arrow is here. This is a different oscilloscope. This is not the one you have in lab. But you can see that the trigger voltage is indicated by this arrow on the right. You can see the horizontal position, that's time 0, where the trigger happens. And there's the arrow right there. And so you can see the trigger voltage crosses that 0-second position right there. Okay, and then I'm also triggering off of a positive slope. You can see the symbol in the lower right. That means a positive slope. It's going from low to high. Right, in the bottom, I still have the same horizontal position. I have a trigger right here. I have the same trigger voltage right here. Okay, but the waveform shifted. That's because I'm triggering off of a falling slope. So here you have a falling edge or a falling slope off of which I'm triggering. Okay, so that's typically what you want to see when you're looking at a periodic waveform. You want to have the trigger voltage somewhere between the min and the max of the voltage you're measuring. Now, if you look on the left here, well, why is this waveform even showing on the screen? It's because I have the oscilloscope in auto mode, auto trigger mode. The scope will trigger even if no trigger voltage crossing is detected. So right here, you can see I have the trigger voltage up here above the waveform. So if I had the oscilloscope in normal mode, you wouldn't see anything on the screen. In normal mode, often, typically, in normal mode, the oscilloscope waits for a crossing to be triggered, and it's not going to show anything on the screen until that trigger happens. In auto mode, usually an oscilloscope waits a little bit. It doesn't see a trigger. It times out. It waits a little bit, and then it just starts randomly triggering, or probably more to the point, periodically triggering. And so you get random starts of the waveform on the left, and then the sine wave is traced out. But every time the scope is internally triggered, there's a different starting point of that sine wave, so it looks like a mess on the screen. Okay. So the trigger source needs to be set to the channel measuring the voltage for triggering. So if I were applying a voltage to channel 1 that I want to measure, this sine wave, let's say, and I'm triggering off of channel 2, no matter where I put the trigger voltage, I'm not going to trigger off channel 1 because I'm set to channel 2. So you have to make sure that your trigger source is set to the channel measuring the voltage off of which you want the trigger. Okay, so some settings. There's some trigger settings. There's a trigger menu. So you can define a trigger type. So here I have the trigger type set to an edge. That means a rising or a falling waveform. And you can see in the menu here, you have edge, you have edge, then edge, you have pulse width. You could trigger off a certain pulse width. With these modern oscilloscopes, you can trigger off of different characteristics of a waveform. You might trigger off of a specific rise time or fall time. Let's suppose you're looking for a very sharp rise time, and every once in a while you get a slow rise time and you want to find that. You can trigger off that here. Okay. The trigger menu defines the source. Right here's the source, channel 1. It defines the slope. I have this on rising edge. And if you tap on that on the oscilloscope in lab, you'll see you can trigger off of rising, falling, and this scope actually lets you trigger off of alternating or either. And then there's a mode and a coupling menu. So down here, you'll see mode and coupling and some other options. Right? That's activated by this button here on the scope that you have in lab. So here's where you can set the auto mode or the normal mode. Remember, in auto mode, even though a trigger voltage isn't crossed by the waveform, it's eventually going to start triggering itself, the scope will. And then in normal mode, it's going to actually wait for a crossing before anything is shown on the screen. You can use AC or DC coupling. DC coupling is what you see on the screen is what the voltage is. And that's what you're triggering off of. You can also trigger off of a waveform that is AC coupled, which means the DC component has been removed. Okay. There are noise reject features often on modern oscilloscopes and high frequency reject. And so if you're having trouble setting up the trigger to get a stable image, even though you know it's a periodic waveform, you know it's a sine wave, but you just can't seem to get a stable image on the screen, it's because you might be triggering off some high frequency noise that's getting in your circuit. So you can try enabling high frequency reject. You can enable noise reject and try that to get the noise out so that the trigger circuit of the oscilloscope or the trigger detection sees a cleaner signal without the high frequency noise. Okay, so often it takes, now that you have just kind of, you've heard these terms and you've seen it, if you have any trouble in lab, refer back to these couple slides and I think you can figure out how to get the oscilloscope to trigger on the waveform that you want to look at and get the view you want of that waveform. All right. Okay, so let's do a clicker problem. So you're using an oscilloscope to measure a ramp waveform, and that waveform looks like this. Okay, so that's all you see on the screen. You can see the trigger time right here. That's that arrow or that triangle. You can see 0 volts on this particular oscilloscope. This shows the channel number and an arrow, and that means that's 0 volts for that channel number. And this is just the center of the time axis here, right? So you can see I have 10 divisions across the screen, and this happens to be just the center center grid line that is a little wider. Okay, and the oscilloscope is set for 1 volt per division and 100 microseconds per division. So the question is, given all this, what trigger voltage and trigger slope are being used? Right, so what is the trigger voltage that's being used? And what is the trigger slope being used? You're kind of reverse engineering how someone set up this scope. Maybe you have a measurement, you can't see the settings, and you're trying to debug a measurement to see if it was right, so you have to back out of the measurement. What was the trigger voltage and what was the trigger slope? All right, let's take a look at this then. So you have this, let's see, a trigger indication here. This is where the trigger occurs in time, right there. That's that trigger time. And so where that trigger time crosses the waveform is right here. So that means that this horizontal green line is the trigger voltage. That's where the trigger occurs. And I'm set up for 1 volt per division, 0 volts. That's right here. Go down one division, that's -1 volt. Okay, and where that trigger is happening is a rising edge. So the answer is -1 volt and a rising slope. Okay, a -1 volt falling slope trigger would look like this. So if I still had a trigger voltage of -1, but I just changed the setting to a falling slope, it would look like this. Okay. Okay, let's talk about oscilloscope probes. So there is an oscilloscope probe. You typically use an oscilloscope probe to connect from an oscilloscope BNC connector. Often these oscilloscopes that are relatively low frequency have a BNC connector. Some of them have fancier connections around that BNC connector or different kinds of connectors because they might be compatible with active probes that have amplifiers built in. But the oscilloscope that you have in lab should just have regular old BNC connectors that look like this. So that probe has a tip and a ground connection. So here's the probe tip. That's the positive of the reference polarity for the voltage you're measuring. And here's the alligator clip that has the ground connection. So typical probes in relatively low frequency non-RF applications have 10x voltage ratios. And they have 10x ratios. That means that the voltage that the scope is actually seeing is 10x different than the voltage that's actually being measured. Okay, and they do this, these probes are like this, so that these probes appear as a very high impedance when connected to a circuit. So you want, when you touch an oscilloscope probe to a circuit, you really want the circuit not to even know it's there. You don't want any kind of current going into the probe, and that would change the circuit itself. That would look like a load on the circuit. So when you have a 10x probe, that actually helps increase the impedance of the probe. And so you use the oscilloscope channel setting, usually, to define what kind of probe you have. Is it a 10x probe? Usually, when you turn on a scope and you set the defaults, it defaults to 10x attenuation for the probe, because it's just common to have 10x probes. Okay, and probes should not be used for other BNC connections. You know, like you have a function generator that outputs a voltage, let's say 0 volts to 5 volts, something like that. And you know, it's tempting to use an oscilloscope probe to take it to connect to the BNC of the function generator and then clip your probe on, because it has nice convenient clips on it, to your circuit. But if you have a 10x probe, you're not going to see on the output of your oscilloscope probe what you expect into the probe from the function generator. So just don't use these as BNC to alligator clip cables. They're not appropriate for that. And also, I tend to not use just regular BNC to alligator clip connectors as scope probes. Again, because of the loading of the circuit at higher frequencies, that can cause a problem. So use a scope probe for oscilloscope measurements and don't use them for anything else. Okay, let's talk about the ground loop trap. Remember I talked about grounding, you know, the isolation of the negative terminal of a power supply from earth ground or from AC ground. This oscilloscope, an oscilloscope is not like that. Typically, the oscilloscope, the shield of the BNC connector is typically AC ground, and it's a common ground with other probe connections. So let me show you an example here. Let's suppose you have a motor that is being controlled by a MOSFET, just like in your project that you're building. So you have the motor, and the MOSFET connects or disconnects the ground from the motor. Okay, and so you want current to flow this way down through the MOSFET when the MOSFET's turned on. All right, let's define a voltage across that MOSFET, VFET. Okay, let's suppose you want to measure that voltage. So you say, oh, I could just take an oscilloscope and connect the tip of the probe here, right between the motor and the FET, and clip the ground lead down here, and that works just fine. Let's suppose that this is truly ground down here at the bottom of the MOSFET circuit, and your oscilloscope also, its ground lead is also ground, and so you can measure VFET like this, and that works just fine. So this will work because the reference for VFET, this voltage, is ground. It is the ground of the circuit. Okay, let's suppose you have the same circuit and you want to measure the motor voltage. So you're going to do this in lab. And so you're tempted to, well, let's just connect the oscilloscope. Let's connect the ground of the oscilloscope here and the tip of the probe here at 5 volts. But the problem is when you've done this and you have this test equipment hooked up and it's all connected to a common ground, you're actually causing a current path. Some people call this a ground loop. You're causing a current path from this junction between the motor and the FET, supplying a ground, and you're causing the motor to actually spin. You've created a ground path for that motor that you didn't want because you're measuring it with the oscilloscope that has a ground lead. Okay, so don't do this. Measuring this voltage directly may cause a ground loop, causes current to actually travel through the scope, through the oscilloscope. And a better way to do this, or a way you should do this, is to measure the difference between two voltages. You can measure VFET, and you can measure VS, and VS minus VFET is the motor voltage. And you can actually use 2 channels of your oscilloscope to measure both of these voltages at the same time. You can measure VFET, and you can measure the power supply voltage. Both channels would have their ground connections to the ground here at the bottom. And then you can use the subtract functions. Most modern oscilloscopes have math functions that you can use for measuring differences. It's one math function, differences between channels. So you can measure VS with channel 1, measure VFET with channel 2, and say, show me channel 1 minus channel 2 on the screen. And the oscilloscope will do that. Okay, so generally use an oscilloscope to measure node voltages. Node voltages are always with respect to ground. Use the probe ground connected to the ground of the circuit. Okay, there are differential probes. There are different kinds of probes out there that you can do these measurements directly, but generally you walk into a lab with a fairly low cost, low frequency oscilloscope, and you're gonna run into these types of problems with basic probes. Okay, so modern oscilloscopes let you save screen captures, let you save data files and configurations. So here's a file menu on your oscilloscope. So common save and recall functions are screen captures for recording views and basic measurements and capturing features of waveforms. So you can see here, you can set up the format for saving. Here's a 24-bit color bitmap image. You can just save the screen to internal memory or a memory stick, or copy to a memory stick later after saving to internal memory. Some oscilloscopes use the save button to save the screen. Some oscilloscopes and different instruments use the print button to save a screen, and the print can be set up to save a file. So you gotta just look in the menus and figure out what your particular instrument does. The data files can be saved for detailed waveform data like voltage versus time, and you can do post-processing on that. You can plot that data, you can analyze that data, you can do math on that data later if you save files like this, like CSV comma separated value files, or ASCII XY data, right, or binary data. You just have to look at the scope help or the manual to figure out what format that binary data is in. I often save CSV data. CSV files are often very easy to read. You can open them up in Excel. You can open them up in MATLAB. They're very easy to open and process. And then you can also save settings of the scope. So let's suppose you're doing your motor project, your constant speed propeller project in lab, and you've got this measurement set up, and you got a class coming up, and you've spent 15 minutes setting up your scope with all the settings to get a clean view of something. Well, what you can do is you can save those settings, save the state of the scope, put it on a memory stick, later come back and recall all those settings. That's pretty useful sometimes. Oscilloscopes have cursors to do measurements and also built-in measurements. So if you go to your scope in lab, there's this cursor button. And you can use these to determine certain characteristics, time or voltage of the waveform you're looking at. And so there are user adjustable cursors. So you turn a knob, you're the user, and you can adjust these cursors to provide relative time and voltage values and absolute time and voltage values. Okay, so you can see right here, these orange lines, they're cursors I have set to measure voltage. So here's Y1 and Y2, one of those, let's see, Y1 must be the lower one. It's at negative 5.14 volts. Y2 is at 5.06 volts positive. You can see delta Y. What's the peak to peak voltage there? It's 10 volts. And also cursors can be used to serve as a reference. So like when you're adjusting something about your IR detector, right? And you're trying to adjust either something in time or something in amplitude, you can put a cursor on the screen and then turn your potentiometer, maybe it's adjusting amplitude, and you can adjust relative to that cursor. It's just like drawing a line on the screen to be able to have a reference point against which to adjust. Now, measurement functions automatically calculate waveform characteristics. So you can see here, you can see you can measure peak to peak voltage, maximum voltage, minimum voltage, amplitude, all these different values. But typically, automated measurements of oscilloscopes include frequency and period, mean voltage, peak to peak voltage, and RMS voltage, minimum and maximum voltage. Also rise times and fall times. If you have like a square wave and you need a certain rise time, a certain slope, you can measure that rise time with the oscilloscope built-in measurement capabilities. Pulse widths can be measured. And also phase and delay. So if you have two sine waves and you want to measure the phase between those two sine waves, you can do that. Or the phase or the delay between two square waves, you can do that. Let's see, I missed someone's question on the multimeter. I'll get back to that, but the question that just popped up, what is the difference between CSV data and analysis results? Let's see, let me go back there. CSV data and analysis results. Okay, I don't understand the question. If you want to clarify that. So CSV data is just the raw data, X and Y positions, right? Voltage and time in rows out of the scope. Further down, analysis results. I don't know what that is, but I'm going to say if you had some function set up that was taking measurements, I think that's what it would do. Reference waveform data, multi-channel waveform data. That must be some kind of special file format. Analysis results in CSV. I don't know what that is. I think that must be the result of some function going on in the scope that you've set up to process in real time as you're taking the measurements. But I'm gonna look at that, figure out what that is. Okay. Now the ubiquitous auto button. Let's talk about this auto set button. Well, let's talk about default first. Many oscilloscopes, many instruments have something, they have default setup, or there's a button called preset, or there's a button called, there's different names for them. But basically these buttons with sometimes different names, they restore the oscilloscope to a known state. It might not be like a factory reset, but it usually resets most, if not all, of the settings so you know where you're starting. So I recommend this whenever you show up at the bench in our lab, and I do this on my equipment back here. I recommend pressing the default setup or the preset button, because this will start the scope or whatever instrument in a known state. Okay, because you don't know what someone before you was doing on that scope, and they turn the scope off and you turn the scope on, and you may have some weird scale settings in there and math settings, and you're looking at the screen, it's not making sense for what you think you should be seeing out of your measurements. I recommend when you walk into lab, hit the default setup, and that will set everything back to a known state. Again, even when I'm using it, and I was the last one using it, I don't know what I did on my last measurement, so I hit default setup. I generally don't use the auto scale button. It's very tempting to do that. I'll say I generally don't. Maybe, I mean, it might be, it's less than 10% of the time, probably less than 5% of the time do I use auto scale. It's very tempting. It's like, hey, the scope's got my back. It's gonna get me set up for a good measurement, but often it doesn't. If you do use it, and when I do use it, I verify that the scales are reasonable. So I kind of know maybe I'm measuring a 60 hertz waveform, and you know that the scale should not be in nanoseconds on the horizontal scale then, right? If I'm measuring something that has milliseconds of periods. Okay, so here's an example. Like this is an example of hitting auto scale with a bad probe connection, right? You're looking, what is this waveform that I'm seeing here that's not really triggered very well either? And well, this is because there was a probe problem. The probe wasn't connected properly to a node, and you hit auto scale, and the auto scale is happy to try to zoom in and set reasonable settings for the waveform it thinks you're measuring. But the problem is sometimes it zooms in on noise and not the signal. Even when the probe's properly connected and you do see the signal, sometimes it zooms in on noise. So be careful with the auto button and always start with default or preset. Okay. All right. So that covers what I wanted to talk about with regard to oscilloscopes. Does anybody have any questions? Anything you want to talk about there, either now or any topics you want to cover in the future about oscilloscope? I hope I clarified some things about triggering and scaling and measurements and settings. Okay, well, if you have any questions, stop by office hours if you want to chat about this. I think instead of starting into function generators and waveform generators, let's end it here for today. We'll continue next time talking about function and waveform generators. But just as a reminder, check Canvas for the due times and due dates for the assignments coming up. There's no homework due this week. It's due next week, Wednesday, 9/25. And also you have a lab this Friday, so I'll see you in lab as we start getting into some of the more interesting work in lab. So I will start office hours in just a few seconds. So if you would like to join, please stick around. If not, I'll see you next time. Have a great night.